In the last video, I did a recurrence relation that ended up having a finite series in the solution. And so that was actually a special type of series called a geometric series. And so in this video, I just want to talk a little bit about geometric series. And the reason is because, not just because it was in the last example, but because we're going to need to know about geometric series coming up here pretty soon to look at some of these other recurrence relations, including the Fibonacci sequence. So if you have a sum where you're adding up numbers to the index power for the index of that sum, they go from 0 to n. This is called a geometric series. And so I'm just going to call this Sn, where n is just the stopping point of the series. So if I wrote this out, this would just look like 1 plus r squared all the way up to r to the n. And so the cool thing about this is that there's actually a simpler form than this thing right here, and you can go back and forth between them. So if I take this whole thing and I just multiply it by r, then I'd have r s of n is equal to, well, you can see what that's doing here is I could just think of this as shifting the indexes all up by 1. So I could start at 1 and go to n plus 1. And then over here, this is just, all of these are just getting multiplied by r. So I have this 1 that's getting multiplied by r. This r gets multiplied by r. Then I'm going to eventually have an rn, and then my top term is now going to be rn plus 1. So what I can do is I can take this one and I could subtract this one. So if I take r sn minus sn, I'll just say r minus 1 sn. This is just going to be rn plus 1. All of these in between terms are going to cancel out except this 1, and so I'm just going to be left with minus 1. And so now I can solve for Sn. So Sn would just be Rn plus 1 minus 1 over R minus 1. And actually in the last problem, the sum that I had didn't go up to n, it went up to n minus 1. So if I wanted to find out what that is, I could just sub in n minus 1 here, and I would see that that's just r to the n minus 1 over r minus 1. So then oftentimes when you're dealing with these geometric series, they're actually going to be infinite series, so you're going to be looking at the limit as n approaches infinity of Sn, which would be the same as the limit approaching infinity on this one here. And so something interesting happens there. If you look at this term, if r is less in magnitude than 1, then this term will go to 0. If it's greater than 1, then it'll go to infinity. So what we can say is this is just going to be, this is going to go to 0. The case we care about is when it converges. So if r is less than 1, then this is just going to be minus 1 over r minus 1, which is the same as 1 over 1 minus r. And this is if r is less than 1. So this is going to come up and be pretty important in some of the later recurrence relations we look at. But the other thing I wanted to mention is, so in the last example, the recurrence relation that I gave was fn plus 1 is equal to r fn plus 1. And so this gave us the solution fn is equal to, let's see, what was it? Let me look over here. It was r to the n f0 plus the sum from 0 to n minus 1 of r to the I. And so what we can do is this this would just be this Sn minus 1 here. So this, another way of writing this solution, if you wanted to simplify it without having a sum in there, you'd have this is r to the n f0 plus, then we just have this thing here. This is just r to the n minus 1 over r minus 1. And so actually there's something interesting about this. If you look at the limit of this sequence, then what's going to happen, this is valid only if r, okay, well this is valid, but if r is less than 1 in magnitude, then this one is going to go to 0, which means this entire term goes to 0. And then over here we have that same thing going on where this goes to 0. So this would just end up equaling 1 over 1 minus r. This is provided that r is less in magnitude than 1. So this is pretty cool. Also notice that the limit of this sequence is not dependent at all on the start point, which is also kind of cool because that means you could start the sequence wherever you want. This would be like an initial condition. You could start it at 100 or something, and no matter what, the limit of the sequence is just going to approach 1 over 1 minus r.